Hey everybody, in this video we are going to talk about reaction mechanisms. Reaction mechanisms are the set of reactions, also known as elementary steps, that chemicals take to reach its products. The coefficient of a step of a mechanism is the order of the reaction and not the coefficient of the overall reactions. So, for example, you are not going to read the net reaction to see what the orders are. Instead, you are going to read the elementary steps, specifically steps 1 and 2. And according to the elementary step 1, the order of NO2 for this particular reaction will actually be 2 because the coefficient is 2. So let's read this and see what's going on. So we have two elementary reactions, when added together, will yield the net reaction, which is written above. So if you notice, our NO3s actually cancel out, and since they cancel out, they are called intermediates. And an intermediate is any substance that is produced and then consumed in a mechanism. They do not appear in the net reaction. Now, catalysts don't appear in the net reaction, but we will talk about those later and how to differentiate intermediates and catalyst. So let's talk about what the forward arrow actually means. So over here we have a forward arrow from A to B, and in these two elementary steps we have two forward arrows. So what does a forward arrow exactly mean? Well, because the two reactions have a single or a forward arrow on it, this means that the forward reactions are spontaneous. In other words, the forward reaction is much faster than the backward reaction, so when you add the two processes together, the net process is the forward reaction, since that reaction dominates over the backward reaction, and overall, when you combine them together, you get a net forward reaction, which is why it is a single arrow. So in this example, you can see that the forward reaction indicated by the forward arrow is much larger than the backward arrow, and because of that, if you add these two arrows together, the net result is that you will get a forward reaction. Now, just because the forward reaction is faster than the backward reaction doesn't mean the forward reaction is fast at all. It is just faster relative to the backward process. So A to B can actually be very, very slow, but the conversion from A to B is much, much faster than the conversion from B to A. So note the difference and don't be tricked by this. Now, because the forward reactions are so much quicker than the backward reactions, which is why you have a single arrow overall, we tend to ignore the rate at which the backward reaction happens and instead only focus on the forward reaction. So all reactions can go forwards and backwards, but sometimes the forward reaction might be much faster than the backward reaction, and because of this, people like to just consider the forward reaction, since essentially you can think of the backward reaction as not existing at all, since it is so small compared to how fast the forward reaction is happening. So we can write rate laws using these elementary steps, and remember, the coefficients in elementary steps can tell us the rate law and the orders of the reactants. So let me show you how that works. So when writing the rate law for a forward reaction, the substances to focus on are the reactants. So if I want to write the rate law for the forward reaction indicated by the rate constant K1, so we are looking at this forward reaction, then the rate law would just be rate is equal to K1 times NO2 squared, since the 2 is the coefficient. So the rate law for the very first elementary step would be rate equals K1 times NO2 squared, with brackets of course. And what about the rate law for the second forward reaction? Well, we look at the reactant, since it is a forward reaction, and rate would be equal to K2 times the concentration of CO times the concentration of NO3. So you get this. And we will see this soon, but if you are writing a rate law for a backward reaction, the substances to focus on are the products. So we will see this later, as I just said. Now, how do we find the rate of the overall reaction, or in other words, the rate of this reaction over here? So to do that, we actually have to do some assumptions. The slowest step is the rate determining step. When writing the rate law for the overall reaction, we typically only focus on the rate determining step. Think about it this way. You have a test to grade and there are 2 steps. The first step takes 5 seconds, such as scanning the paper, but the second step takes 40 minutes, or reading the paper. So, grading a paper will take 40 minutes and 5 seconds because the time it takes to read and scan the paper will be the time it takes to do the entire process. But since that 5 seconds is so tiny compared to the 40 minutes that you took to read the test or the paper, then we essentially say that the time it takes to grade the test is the time it takes to read the paper. So essentially we focus on the second step, which is reading the paper, and that takes 40 minutes. So we have to do the same thing here. We have to look at the slow reaction and base our entire reaction rate of the overall reaction on that slow step. So according to the problem, step 1 is the slow step. So we have to focus on the rate law for the slow step, and that rate law of the slow step will be the rate law for the entire reaction based on our assumption we just made. So, since the overall rate of a reaction is essentially the rate of the slowest reaction, and we know that the rate of the slowest reaction has this rate law, then the rate law for the entire reaction is essentially the rate law of the slowest reaction, and we found that here. So therefore, the rate for the reaction is equal to K1 times NO2 squared, essentially. So this is essentially the rate law. We are basing it off of this assumption that we made up here. Alright, now what if the forward reaction and the backward reaction are equal in rate? Or in other words, the reaction overall is in equilibrium. So the first elementary step is the equilibrium reaction, and the second step is going to just be a forward reaction. And notice how for the equilibrium reaction, there's a K1, which is the forward reaction, and the K negative one, which is the inverse reaction or the backwards reaction. And for the elementary step 2, notice how it's just the forward reaction, indicated by the rate constant K2. When you add these two up, you get this as the net reaction, and you notice that NaCl2 cancels out, and this tells us that NaCl2 is an intermediate. So, we essentially have 3 rate laws that we can write. There are actually 4, but the backward reaction for step 2 is so small, as I mentioned in the previous slide, that we don't care about it. So, how do we write these rate laws for the 3 reactions? Well, we could write a rate law for the forward reaction indicated by K1. So, rate indicated by K1 is equal to K1 times NO times Cl2. Now, what about the backwards reaction? Well, as mentioned before, if you're writing a rate law for a backward reaction, the substances to focus on are the products. So if we want to write the rate law for the backward reaction of the first step, then what we do is that we multiply K with the subscript -1 by the products, which is NaCl2, right there. Now what about the rate law for K2? Well, that's equal to K2 times the reactants, NaCl2 and NO. So notice how these are all first order because the coefficients in front of everything that we're looking at so far are 1. Now let's continue. Reaction 1 is at equilibrium. Therefore, the forward rate and backward rates are the same for step 1. So we could say that the rate of the forward reaction indicated by K1 is equal to the rate of the backward reaction indicated by K -1, since that's what it means to be at equilibrium. So you could substitute the rates for the rate laws and you get this is equal to this. Now, we need the rate determining step since we want to know the rate law of the reaction. So the rate determining step is the slowest step. That would be step 2 because step 2 is indicated by the word slow. So the rate law of the entire reaction will be the rate law of step 2, which turns out to be this, and thus the rate law of the reaction turns out to be the same thing as the rate law for K2. Now this rate law is perfectly fine, but it would be better if we didn't have an intermediate in there, because scientists can't measure intermediates as well because they are unstable, or in other words, they disappear as soon as they appear. Especially in very fast reactions like combustion, or maybe even this reaction. So we only want things that we actually can measure effectively. Or in other words, the stuff in our rate law should belong in the net reaction, or in other words, it should have either NoCl2 or NoCl. So something like NoCl2 is hard to measure, so we want to substitute that for something else. So we're going to do some substitution. We have an equality here, and we see that there's an NoCl2 here. We could use that to our advantage by doing some algebra and finding that the concentration of NoCl2 is equal to all this stuff. And we can just chug this into here and substitute this for this. And you end up getting that the rate law of the reaction is equal to all this stuff after simplification. So this K2, K1 over K negative 1 can be hard to read, so you can actually condense this into simply just K. But if you want to be specific and label the K's of the reactions, then I would keep it like that. So now that we're done with that, let's do a case study. Let's analyze the catalysis of H2O2 via potassium iodide. So 2H2O2 becomes 2H2O and O2 with the help of an iodide catalyst. So when you write catalyst, you put it on top of the arrow most of the time. So here's the mechanism, and it involves 2 steps. And as you can see, the first step is the slow or the rate determining step, and step 2 is the fast step. So let's identify the intermediate. The intermediate will be IO-, or the hypoiodite ion. And it is an intermediate because not only is it not in the net reaction, which is this, but also as soon as it is produced, it is consumed. So it's produced here, it's consumed here. Now, which one is a catalyst? We know that I- is a catalyst, but why is that? Well, immediately when we put I- in, it gets spit back out. So it gets put in here and it gets spit back out. And overall, it's not consumed in the reaction. But the difference between an intermediate and a catalyst is that while an intermediate is produced and then consumed, a catalyst is put into a reaction and then spit back out. But a similarity between the two is that they are not found in the net reaction. So that's all for that part, and now let's try to find the rate law. The rate law will be the rate determining step, so the rate determining step will be the slow step, and thus we have to find the rate law of the slow step to get the rate law of the reaction. So the rate law of the slow step is going to be Ki times the concentration of I- times the concentration of H2O2, and you get that. Now, you're wondering, there's a catalyst in the rate law? How is that possible? Well, that's actually fine, because we can actually measure the concentration of catalysts that aren't used up in a reaction. So because catalysts aren't used up in a reaction, we can measure them, and because of that, we can keep it in the rate law if we want. Now, this reaction is special because it is used in a demonstration called elephant's toothpaste. Elephant's toothpaste is when you mix hydrogen peroxide with some potassium iodide or any salt that has iodide dissolved in water, and you also add some soap and maybe even food coloring as shown here. So bubbles produced from the reaction, and this reaction produces O2 gas as shown there, causes the soap to bubble up and turn into foam, which is why you see a bunch of foam being produced here, which is pretty cool. And before we continue, let's find out why this is a net reaction. So I cancel out the I- and the IO-, and you end up getting 2H2O2 becomes 2H2O and O2. So it's kind of like Hess's law if you think about it. Now let's talk about a special concept known as steady state concentration. This occurs when the concentration of a substance, or maybe more than one substance, is being consumed at the same rate as it is being produced. So in other words, the concentration of the substance will be constant. So let's see what this actually means. So before we continue, you might think that these are in equilibrium, so A is in equilibrium with B. Well, you could assume that, but I will tell you explicitly here that you cannot assume that these two rates are equal in this reaction. So since I'm telling you, then I'm telling you that this is not at equilibrium. But if I didn't tell you this, or you pretend that this message didn't exist, then you can assume equilibrium. But since I told you that they are not at equilibrium, since two arrows are not the same, then that means that you can assume that they're in equilibrium. So, therefore, let's just continue and figure out some things. So B is an intermediate since it is produced and then consumed, and our net reaction is just A to C. So, the question says B is at a steady state concentration. Write a rate law describing this process. So we don't know which one is a fast or slow reaction, so we can't just write a rate law right away. So we have to get a bit creative here. So since B is at steady state concentration, that means that it is going to be constant throughout this process, or in other words, the rate at which it is being consumed is the same as rate at which it is being produced. So, if B stays the same, this means that the rate of production of B, so which reactions produce B? Well, K1 produces B because it goes from A to B. So I would say that the rate of K1 is the rate at which B is being produced, and this is set equal to the rate of consumption of B. Now, what two things make up the consumption of B? Well, B is being lost when it is converted back to A via the backward reaction indicated by K-1, and it is also consumed by the reaction indicated by K2. So, these two rates added up will equal the rate at which B is being consumed. So the rate of the backward reaction of reaction 1 plus the rate of the forward reaction K2 that is consuming B as well will get you the overall rate of consumption. Now, how could I add these rates? Well, let's think about it this way. The rate at which B is lost is equal to the rate at which B is being lost and converted to A, plus the rate at which B is being lost and converted to C. So the two processes of B being consumed combined together will get you the total rate of consumption of B from both reactions combined. So that's why I could add it. So, in other words, if we substitute these rates for their rate laws, we get that this is equal to this plus this. Now, although we don't know the slowest step, we usually never base our overall reaction on the step in equilibrium. So, let's base it off the forward reaction. So, the rate law of the forward reaction, which is this one right here, is just K2 times the concentration of B. Now, we don't like intermediates since B is an intermediate, so we could substitute it. And we have a nice equality here, so let's abuse this equality and factor it, and then find a way to make the concentration of B equal something. And it turns out that the concentration of B, using some algebra, is equal to all this stuff. And notice how we could substitute this stuff for the concentration of B, and we get that the rate of the reaction is equal to K2 times K1 times the concentration of A over K-1 plus K2. So that's pretty cool, right? Now, let's look at our reaction coordinate diagram once again, but let's include intermediates. So we have the decomposition of hydrogen peroxide once again, and I'm going to draw you the reaction coordinate if there was no catalyst. So assuming that the process is a one-step process from H2O2 to H2O2, and let's just assume that, then there will be only one reaction occurring, which is this reaction. So this black outlined curve will be the normal reaction under normal conditions where there are no catalyst. And notice how the activation energy is labeled here. And remember, the activation energy is just the energy difference between the peak and the things that are reacting. So this length over here will be EA. Now, our delta H will be negative because notice how the products are lower in energy than the reactants. So overall, the reactants are losing energy to become the product, so it's an exothermic reaction. And notice how I labeled the reactants here, which is just 2H2O2, and the products are 2H2O plus O2. So now let's look at the catalyzed reaction. So this catalyzed reaction is a two-step reaction. So here's a fun tip. The number of reactions equals the number of peaks you have. So for the one without a catalyst, notice how it's just one big peak. But if you have two reactions, then there will be two peaks. And since this is a catalyst, and remember, a catalyst lowers the activation energy. And in this case, a catalyst is I minus, remember from a few slides ago. And because of this, notice how the activation energy now is a lot lower than before, which means that the reaction rate will increase because of this catalyst. But there are actually two processes. The first process is the slow process, and it's indicated by this first bump. And then there's a second bump here, and the second bump represents the second reaction, which is a lot faster. Now, how did I measure these activation energies? Well, the activation energy for the first step is just the difference between the peak and the reactants. So it's this entire thing. Now, what about the second step? How did I find the activation energy for step 2? Well, the point over here is known as the place where the intermediates are. So in this case, our only intermediate will be IO minus, and this IO minus will react with H2O2 on this reaction pathway, which is the second bump to produce some of our products. And note that our first reaction already produced some of the products. More specifically, the first reaction already produced H2O. So the second step, or the second bump in the curve, will represent the production of our other two products, as well as the return of our catalyst being spit out. So before we continue, I want to remind you that the curve down here, this blue curve that goes up and down, is the catalyzed path, while the black path is known as the path with no catalyst, or no I minus in this case, since I minus is the catalyst. So notice how the second activation energy is simply the difference in energy between the peak, which is over here, which I will label in red actually, and the energy of the intermediates, which is over here between the two bumps. So why is the first activation energy higher than the second activation energy? Well, slow reactions typically have higher activation energies. Therefore, the activation energy of reaction 1, which is this one over here, is higher than the activation energy for reaction 2, as shown in the picture, because the activation energy for the first reaction is a lot higher than for the second reaction, which is a lot lower. And notice how this corresponds to the description, saying that the first step is slow while the second step is fast. So slow equals high activation energy, and fast equals low activation energy. Now, at that point, or at the point where the intermediates are, which is after the first reaction or the first hump, 1H2O2 has already produced 1H2O. So 1H2O2 has already produced 1H2O, which will appear in the products. IO minus is also there as an intermediate that is about to go into step 2. So in between the two humps, you have some IO minus that's about to go into step 2 and react with another mole of H2O2. So now we need to talk about what an activated complex is, because you see that on the graph and you don't know what it is. So the activated complex, as you can see, are the humps or the peaks of the curve. So these peaks have something called an activated complex. Now, an activated complex is just an assembly of atoms that are clumped together and are about to swap atoms. These complexes are unstable and thus have very high energies, and you can see that because on the graph, these activated complexes are at very high energy states. So what I did here is that I kind of zoomed in, and I zoomed in to here. So I circled the place where I zoomed in, and this is the zoomed in place. And the first hump shows the first step, and in the first step, H2O2 plus I minus becomes H2O and IO minus. So I drew some pictures. I drew an H2O2 and I minus reacting. So when they're reacting, they are reacting and they are forming an activated complex, which is labeled with this symbol, and this symbol is a double dagger symbol, and this is just the symbol for an activated complex. So as you can see in this activated complex, they are together. So I'm just making this up and assuming that the activated complex is when the H2O2 is connected to the I minus and like right next to it. So I wrote H2O2 I minus as if they were all in one piece. And then after some time, it falls down in energy and it splits into H2O and some IO minus. So notice how it goes from reactants over here to products, and right in between we had an activated complex. Now over here, this place where I'm circling right now, this is where the intermediates are, because the reaction is not done. There's still another hump that we have to go through before we finish this reaction. So reading this graph, we can see that regardless of whether the reaction has no catalyst or has a catalyst, you notice how the delta H stays the same. Or in other words, the difference in energy between the products and reactants stay the same, no matter what path you take. And this should remind you of Hess's law and the idea that enthalpy is a state function. But what's different is that for a catalyzed reaction, the humps are lower and the activation energies are lower than for the uncatalyzed reaction, and you will see that for all catalyzed reactions. Now, if you're wondering, another word for an activated complex is its transition state. So that's just a fun fact. And now let's do some reviewing. So at the beginning, we have reactants, and at a peak or hump, we have our activated complexes. And in between humps, we have our intermediates, and at the end, we of course have our products. And the activation energy is measured by going from the hump to the nearest substances that are going to react. So in this case, the substances that are reacting are the reactants, and it's going up to the hump. So this difference in energy is the activation energy. And in the case for the second curve, which is covered by a bunch of letters by now, is over here, so I'm trying to circle it. The activation energy for the second part of the reaction is going to simply be the difference in energy between the hump and the energy of the intermediate. So this difference will be EA2. And last but not least, the difference in energy between the reactants and products will be the delta H, as shown with this over here. And that's all for this video. I hope you learned a lot and have a nice day.